Well, we're going to get started here. So today we will be getting into section 11.2. Considering we did 11.1 last week. Hopefully y'all had a great weekend and that your day started well, that you're feeling good today. And hopefully this lesson goes all right. It shouldn't take too long. It's not too bad. Again, it's kind of just a big chunk of information. We're going to get through our PowerPoint presentation, discuss a couple other chi-square tests having to do with two-way tables instead of a one-way table, which is what we saw in section 11.1. And we're just looking at one categorical variable, right? So in this case, we're going to be looking at two-way tables and inference for those two-way tables. Yeah. So also before we get started, all the resources for chapter 11 are available in Canvas. You have your like notes and resources like the study guides, those are ready. All the videos, AP Daily from the textbook, all those things. The practice problems and solutions are ready for section 11.1 and 11.2. So you have all of those available to you. So go ahead and check those out if you like. That being said, we're going to get ourselves going here. So I'm going to share my screen. And there we go. All right, so if at any point along the way you have questions, comments, concerns, please let me know. Raise your hand, shout at me, something. If you need me to slow down, let me know. If you're writing stuff down, let me know. So here we are in chapter 11. 11.2 is inference for two-way tables. Right, two-way tables allow us to show distributions of categorical variables, and we'll be working with those. In this lesson today, we're going to learn how to compare conditional distributions for data in a two-way table, state appropriate hypotheses, and compute expected counts for a chi-square test based on data in a two-way table. Calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test based on data in a two-way table. We need to be able to perform a chi-square test for homogeneity and a chi-square test for independence. And we should be able to choose the appropriate chi-square test based on a given context. The two sample Z procedures of chapter 10 allow us to compare the proportions of successes in two populations or for two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables have more general uses in comparing distributions of single categorical variable. They can be used to describe relationships between any two categorical variables. All right, market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the numbers of customers who ordered French, Italian, and other entrees. And we have these observed data points here. Right? When there's no music, we had 30 people order French, 11 Italian, 43 other. With the French accordion, we got 39 French, 1 Italian, and 35 other. And with the Italian string music, we had 30, 19, and 35. All right. So we have all of our observed data here. We want to calculate the conditional distribution in proportions of the entree ordered for each treatment. Right, when no music was playing, the distribution of entree orders was French was 0.357, Italian is 0.131, and other was 0.512. When we get that French accordion music playing, the distribution is French of 0.520, Italian 0.013, and other 0.467. And lastly, when we have our Italian string music, the distribution of entree orders is French of 0.357, Italian of 0.226, and other 0.417. So we have our conditional distributions, right? The condition is the type of music, all right? And so that's how we get the denominator values essentially, right? 84, 75, and 84. Right, the totals from the three different columns. Right, we can make an appropriate graph for comparing the conditional distributions in part A. In this case, they're showing bar graphs. Represent one set of bar graphs for each type of music and the distribution of entrees ordered based on that category. And we can kind of quickly compare these things visually. So we can write a few sentences comparing the distributions of entrees ordered under the three music treatments. Type of entree that customers buy seems to differ considerably across the three music treatments. Orders of Italian entrees are very low, 1.3% when French music is playing, but are higher when Italian music, 22.6, or no music, 13.1 is playing. French entrees seem popular in this restaurant as they are ordered frequently under all music conditions, but notably more often when French music is playing. And lastly, for all three music treatments, the percent of other entrees ordered was similar. We're just making a quick comparison. Just what we see in the graphs. The problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is common in statistics. This is the problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have two parts. Number one, an overall test to see if there is good evidence of any differences among the parameters that we want to compare. And number two, a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test uses the familiar chi-square statistic and distributions. We'll get to a follow-up later. All right, so we need to be able to get our expected counts in order to do a chi-square statistic. Chi-square test for homogeneity begins with the hypotheses. Right, the null hypothesis, there is no difference in the distribution of a categorical variable for several populations or treatments. And the alternative is that there is a difference in the distribution of a categorical variable for several populations or treatments. We compare the observed counts in a two-way table with the counts we would expect if the null hypothesis were true. Again, remember our expected counts is using the assumption the null hypothesis is true. Right, consider the expected count of French entrees bought when no music was playing. Right, we have 99 over 243 times 84 equals 34.22. So we take the row total from French, the column total for no music, and the sample, like the total size of the sample essentially. All right, the table total. All right, and those three numbers are used here. The values in the calculation are the row total for French, the column total for no music, and the table total. We can rewrite the original calculation as, right, row total times column total divided by table total. Right, and that equals 34.22. We would do these same calculations for each entry in this table to get our expected count for each of the entries. Overall, that would be 9 calculations. All right. Is there any questions about this part, the expected counts for this example? All right, so we have expected counts in the chi-squared statistic, right? Finding expected counts. This goes for test for homogeneity or test for independence. We'll use the same way of calculating our expected counts. When the null hypothesis is true, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. And since we're performing an inference, we have conditions for performing a chi-squared test for homogeneity. Number one, it must be random. The data come from a well-designed random sample or from a randomized experiment. 10% when sampling without replacement, check that the sample size is less than or equal to 10% of the population. And our large counts, all expected counts, are greater than 5. All right. Anyone like a moment to write anything down from this screen? Raise your hand. All right. Just as we did with the chi-squared goodness of fit test, we compared the observed counts with the expected counts using the statistic chi-squared equals the sum of the observed minus expected squared divided by expected. This time the sum is over all cells, not including the totals, in the two-way table. We have our two tables below, the observed counts and the expected counts. We have 9 entries in each of these tables. For the French entrees with no music, the observed count is 30 orders, and the expected count is 34.22. The contribution to the chi-squared statistic for this cell is 30 minus 34.22 squared divided by 34.22, which gives us 0.52. The chi-squared statistic is the sum of 9 such terms, again, because we have 9 terms in our table when we do not include the totals. Please do not include the totals. All right, and then ultimately we get chi-squared equals observed minus expected squared over expected, and the sum of all those, we get a bunch of entries here. It is okay to show that you're doing this calculation and not show each of the parts of this when you write it down. You don't need to show the 9 different fractions. It's okay to do the first couple, put the little dots in between and show the last one, and then ultimately show your total. Right? It's possible for the calculator to do this for us and shoot out that chi-squared statistic for us. We'll see a video on how to do that tomorrow. in our practice stuff. I think this video is only like a couple minutes long. All right. Ultimately, we get a chi-square statistic of 18.28. So we have any questions about this step here, calculating our chi-square statistic? All right, earlier we started a significance test of the null hypothesis. There is no difference in the true distributions of entrees ordered at this restaurant when no music, French recording music, or Italian string music is played. The alternative is there is a difference in the true distributions of entrees ordered at this restaurant when no music, French recording music, or Italian string music is played. Notice there is really only a one word difference between these two hypotheses. First one says there is no difference. The second one says there is a difference. Other than that, they are word for word the same. All right, copy paste. We have our observed counts in the table below. We already checked that the conditions are met. Our calculated test statistic was chi-squared equals 18.28. We use table C to find the p-value, and then use the calculator to get the chi-squared CDF command to get the chi-squared value, or the p-value. And again, we'll see this tomorrow in the calculator. Because the two-way table has 3 rows and 3 columns that contain the data from the study, we use a chi-square distribution with degrees of freedom equaling 3 minus 1 times 3 minus 1, which is 2 times 2, and that is 4. Right. To get the degrees of freedom, you take the number of rows minus 1 times the number of columns minus 1. Right. That gives us our degree of freedom, which we then use on table C to get the p-value. This little excerpt of table C shows degrees of freedom 4, and that our 18.28 is between 16.42 and 18.47. The chi-squared, the value of chi-squared equaling 18.28 falls between the critical values of 16.42 and 18.47. The corresponding p-value, and that's a typo here, guys, I apologize, I didn't fix it yet, is between 0.0025 and 0.001, as it shows on the table up here. Using the calculator, we have the command chi-squared CDF. Right, and then we put in the chi-squared statistic value as the lower bound. The upper bound is just a big old number, 1,000 in this case, because remember our chi-square distributions basically just test for the proportion under the curve greater than a certain value. So it's always just going to be greater than. So we just do 1,000 up there, and then degrees of freedom equaling 4. And this gives 0.0011. Which, looking at the table, makes sense because 18.28 is really close to 18.47. So we should get a value pretty close to 0.001. So any questions about this step in the process? So now we want to interpret the p-value from the calculator in context. Interpreting the p-value in context is not the same as writing a conclusion. Notice that writing a conclusion is the next thing that we're going to do. If you're asked to interpret the p-value in context, you need to write something similar to this. Assuming that there is no difference in the true distributions of entrees ordered in this restaurant when no music, French recording music, or Italian string music is played, essentially assuming the null hypothesis is true, there is a 0.0011 probability of observing a difference in the distributions of entrees ordered among the 3 treatment groups as large or larger than the ones in the study. Okay, so that's the interpretation of the p-value. Essentially, that's what the p-value represents. And then what conclusion would you draw? Because the p-value, 0.0011, is less than our default, alpha equaling 0.05 significance level, we reject the null hypothesis. We have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played. Okay, so we can say a little bit extra there because we used random assignment, and that allows us to do a certain type of inference. Is there any question about the difference between interpreting a p-value and then writing a conclusion based on a p-value? So then we have the rundown here on how to conduct a chi-square test for homogeneity. And suppose the conditions are met. You can use a chi-square test for homogeneity to test the null hypothesis that there is no difference in the distribution of a categorical variable for several populations or treatments, versus the alternative that there is a difference in the distribution of a categorical variable for several populations or treatments. You need to start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-squared statistic, right, where the sum is over all cells and not including totals in the two-way table. If the null hypothesis is true, the chi-squared statistic has approximately a chi-square distribution with degrees of freedom equaling number of rows -1 times number of columns -1. The p-value is the area to the right of the chi-squared under the corresponding chi-squared density curve. Okay. A lot of this at this point, once we have our statistic and we find the p-value, is the same steps as we saw in section 11.1, and getting to our conclusion, we use the same general rules, right? If our p-value is greater than alpha, we fail to reject. If it's less than alpha, we reject. Right? All these same rules apply. We're just looking at a slightly different context. So anyone need a moment to write anything down from this screen? Please raise your hand. Because we found a significant result, we can do a follow-up analysis. Right? The chi-square test for homogeneity allows us to compare the distribution of a categorical variable for any number of populations or treatments. If the test allows us to reject the null hypothesis of no difference, we then want to do a follow-up analysis that examines the differences in detail. So again, we found a significant result. We rejected the null hypothesis. We're going to start by examining which cells in the two-way table show large deviations between the observed and expected counts. Then look at the individual components to see which terms contribute most to the chi-square statistic. All right, and we have this table of information here where expected counts are printed below observed counts. So 30 is an observed count, 34.22 is expected. And the chi-square distributions are printed below expected counts. So we have kind of all the information for all 9 entries in our table. Looking at the output, we see that just 2 of the 9 components that make up the chi-square statistic contribute about 14, almost 77% of the total chi-square equaling 18.28. Right, within these 2, we get 7.672 and 6.404. The rest of them are all considerably smaller. Right, we are led to a specific conclusion. Orders of Italian entrees are strongly affected by Italian and French music, right, because that's where these things are. So we can make up an additional follow-up analysis to give even more information in our conclusion. So next we want to consider relationships between categorical variables. This will be our chi-square test for independence. Okay, the previous example we just saw was chi-square test for homogeneity. Okay, this is for independence. One is checking for a difference between observed and expected. This now is checking for an association. Right. Another common situation that leads to a two-way table is when a single random sample of individuals is chosen from a single population and then classified based on two categorical variables. That's the other main difference between these two contexts for the two types of inferences we're looking at. This is from a single population that is then broken into categories. The previous test is based on independent populations or separate groups. And then we're seeing how they fall into those categories, independent of each other. In that case, our goal is to analyze the relationship between the variables. Our null hypothesis is that there is no association between the two categorical variables in the population of interest. The alternative hypothesis is that there is an association between the variables. Again, we're looking for association. Is one of these things having an impact on the other thing? The chi-square test for independence. The 10% and large counts conditions for the chi-square test for independence are the same as for the homogeneity test. There's a slight difference in the random condition for the two tests. A test for independence uses data from one sample, but a test for homogeneity uses data from two or more samples or groups or treatments. All right, so we have the random condition data come from a well-designed random sample or from a randomized experiment, 10%, sampling without replacement. Check that n is less than or equal to 1/10 of n, and our large counts, all expected counts are greater than 5. Would anyone like a moment to write anything down from this screen? Please raise your hand. All right. So this is the basic rundown again for how to conduct a chi-square test for independence once we've checked our conditions. Right? Suppose the conditions are met. You can use a chi-square test for independence to test the null hypothesis that there is no association between two categorical variables in the population of interest versus the alternative that there is an association between two categorical variables in the population of interest. We're going to start by finding the expected count for each category, assuming the null hypothesis is true. We use the same exact strategy we did in the previous example for finding our expected counts. Row total times column total divided by table total for each entry. Okay. We then calculate the chi-squared statistic as we have for the previous types of problems. Chi-squared equals the sum of the observed minus expected divided by expected, or observed minus expected squared divided by expected, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, the chi-squared statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. The p-value is the area to the right of chi-squared under the corresponding chi-squared density curve. Right, so again, similarly to what we saw with our goodness of fit test, and obviously for the test for homogeneity, degrees of freedom are based on essentially the number of categories, not the sample size. Right? For the test for homogeneity in a two-way table, essentially test for homogeneity, test for independence, number of rows minus 1 times number of columns minus 1. The goodness of fit test in a one-way table, it's just the number of categories minus 1. Okay. Would anyone like a moment to write anything down from this slide? So here we have an example, choosing the right type of chi-square test. Are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. So we have the male, female across the top, fright symptoms, yes or no, on the left-hand side. They used some fancy software called Minitab to output it for a chi-square test using these data as shown below. Once again, we have observed, expected, and then the contribution to the chi-squared statistic. This also gives us the chi-square statistic, which is 4.028. We have degrees of freedom equaling 1. We had 2 minus 1 times 2 minus 1, which is 1. And our p-value is 0.045. We're going to assume that the conditions for performing inference are met. We want to explain why a chi-square test for independence and not a chi-square test for homogeneity should be used in this setting. Right. And that's because the data were produced using a single random sample of college students, who were then classified by gender and whether or not they had lingering fright symptoms. The chi-square test for homogeneity requires independent random samples from each population. So had we stratified the population of students at this college and then randomly sampled from men and women, or male and female students, that would then be a chi-square test for homogeneity, because we first separated the populations and then sampled from the separate populations. But because we randomly sampled from the larger population and then categorized between males and females, it becomes this test for independence. Right. And we're trying to find an association between fright symptoms and gender. Is there anything I can clarify about that? Right. So the next part is state an appropriate pair of hypotheses for researchers to test in this setting. And we have a null hypothesis that there is no association between gender and ongoing fright symptoms in the population of college students. And our alternative hypothesis is that there is an association between gender and ongoing fright symptoms in the population of college students. Again, these statements are almost identical. The only thing different is saying there is no or there is an. After that, they're identical. Which cell contributes most to the chi-square statistic? In what way does this cell differ from what the null hypothesis suggests? And again, we're looking at that summary of the data from their fancy software. Men who admit to having lingering fright symptoms account for the largest component of the chi-square statistic. At 1.883 of the total 4.028. We have 1.883 is twice as large as the closest other contributors. Far fewer men in the sample admitted to fright symptoms, 7, than we would expect if the null hypothesis were true, 11.69. Okay, so this is just kind of observing what's contributing and how is that different from what we would expect if the null hypothesis were true. So now we want to interpret the p-value, which again we already have here, 0.045, in context. Then what conclusion would you draw at an alpha equaling 0.01 significance level? So there are two parts to this answer. Interpreting the p-value, which What does it mean in context? What does it represent? Then stating your conclusion based on that p-value. So if gender and ongoing fright symptoms really are independent in the population of interest, meaning if the null hypothesis were true, there is a 0.045 chance of obtaining a random sample of 117 students that gives a chi-square statistic of 4.028 or higher. That's the interpretation of the p-value in context. Then we have the conclusion. Because the p-value, 0.045, is greater than 0.01, our significance level, we would fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and fright symptoms in the population of college students. Right, so there are two parts to that when you're asked to interpret the p-value in context and then write your conclusion. Again, is there anything I can clarify on this? Okay. So that brings us to the end of this presentation. All right. We can compare conditional distributions for data in a two-way table. We know how to write our hypotheses, or at least we've seen how to write the hypotheses, and compute expected counts for a chi-square test based on data in a two-way table. We can calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test based on data in a two-way table. We can perform a chi-square test for homogeneity and a chi-square test for independence. Now I want to point something out. The way that you do all the calculations, whether this is a test for homogeneity or test for independence, is the same. Same steps, same calculations, same type of stuff will go into your calculator. The only difference is how you write your hypotheses and how you would word your conclusion, right? And how you would interpret in context. The calculations themselves are identical, no matter which form of inference you're performing, which test you're doing. It's just knowing how you're going to write your hypothesis. Are you saying there is an association or not an association? There is a difference or not a difference, right? Those are the major differences between these two. The calculations are the same. Right. Which makes this last part important. Choose the appropriate chi-square test because it means just identifying the context properly. Right. And that brings us to the end of the slideshow. Stop sharing my screen here. All right, so you can find that PowerPoint presentation already linked in the calendar on my Canvas page. It is also linked in the notes and resources for section 11.2 in the module. And like I said, there are practice problems for section 11.1 and 11.2 in our resources for chapter 11 in the last unit module, as I called it, because we're doing 11, 12, and 3 in that module. And lastly, there is still a chunk of you who have not yet checked to make sure that the AP testing app is working or logged in or any of that on your computer, right? That means those of you I'm talking about, you're registered to take the AP exam, right? You must check to make sure that that app is loaded on your computer. If you have a school issued device, make sure that it is loaded and that it works, that it will run. Some of the computers from school are too old to run the app. They will not download it at all. If you have not checked for that yet, it will really suck to be a day or two before your first AP exam, especially if you're testing in other classes besides this one, and not have a device that works, and then having to scramble to figure out how you're going to take your test. You need to check for this now, like today, to make sure it works. If you're on a school issued device, like if it's one of the little silver Chromebooks, like Samsung Chromebooks, I have not seen one of those run the app yet. If you have one that does, somehow you got one that's still able to run it. All right. So if you have one of those and you haven't checked yet, chances are the app probably isn't going to work. So please check for that. Okay. I'll keep checking my list to see who has or has not logged in. You have to log in using your AP Classroom like login, your College Board credentials. Logging in confirms that the download worked. Otherwise, you may have downloaded it, but it might not run. Okay, so please do these steps. Right, I'll be reminding you again at some other point in time soon. Right. If there are any other questions, comments, or concerns, please let me know. Stick around right here, right now, and ask, or send me an email, send me a message. Grades have been updated as of like 1 o'clock yesterday. All right, so you can check your grades to see how that is. I included Chapter 10 assessments in there, so there are placeholder grades in for Chapter 10 things if you have not done them yet. All right, I want you guys to have a good idea of what your grade is right now before the last set of assessments happen at the end of the semester. Okay. So if you have any questions about that, please let me know. Other than that, I hope you all have a great rest of your day, and I will see some of you in person tomorrow, but I'll see all of you in class tomorrow. So have a great day.